of Engineering and Technology. We are learning the subject Basic Electrical Engineering, where we have been discussing about the transformers. Right, you can see here as part of the transformer, we have already discussed about the magnetic materials and BH curve. Then we have discussed about the transformer and its construction. Then we have gone through working of transformer and EMF equation. Then three-phase transformer. In our today's session, we are going to discuss about the ideal transformer and practical transformer. Then lastly, we are going to discuss about the auto transformer. So let us start and discuss about the ideal transformer and a practical transformer. So as we know, the ideal transformer, what they are going to offer? They are going to offer a zero flux. That means the fluxes produced by primary and secondary currents are confined within the core, right? So here they will offer a zero value of flux. Same way the windings have no resistance because this is ideal. So in ideal condition, the resistance of primary and secondary winding both are zero. So here the induced voltage equal the applied voltages, right? So the core has infinite permeability as the reluctance of core is zero and the negligible current is required to establish the magnetic flux, right? So here very small amount of current is required to produce a magnetic flux. As such, the value of reluctance becomes zero for a ideal transformer. Same way here is a lossless magnetic core where no hysteresis or eddy currents are there, right? So it is completely a lossless transformer where there is no copper loss and there is no core loss, right? So if we further talk about the working operation or working of ideal transformer, let us discuss that particular portion. If we talk about this particular symbol, where you can see this is a symbol of transformer where at one end there is a primary winding and another end there is a secondary winding. So here the source is connected to the primary winding and the load is connected to the secondary winding, right? When you apply a V1 AC sinusoidal signal, there is a flow of current IM in this primary coil, right? So from in this primary coil there is an induction of E1, right? So here we need to first understand the working of this ideal transformer with no load, as there is no load is connected at the secondary winding. So one by one, if you discuss about the working operation of this ideal transformer, where you can see V1 is called the supply voltage, V2 is called the output voltage, I1 is no load input current, I2 is output current, IM is called the magnetizing current, and E1 is self-induced EMF in a primary winding, and E2 the mutually induced EMF in a secondary winding. So let us discuss about the working of this transformer, where you can see if you apply the V1, then the current IM flows in a primary winding. So here current magnetizing current IM flows in a primary winding and that will produce magnetic flux in a nearby primary winding, right? Now because of the production of magnetic flux, there is an induction of E1 in a primary winding, right? Same way here magnetic flux phi is also linked with the secondary winding. As per the electromagnetic induction Faraday's law, that flux is also linked with the secondary winding and there is again induction of E2 in a secondary winding. So here the EMF will be induced in a secondary winding as E2, and as such there is no load is connected, so you can say here the I2 is not flowing through any load, so I2 is equal to 0. So here V2 is same as E2 and this is same as E1. So now this would be, we have to depict it in form of the phasor diagram. You can see here a small magnetizing current which is passing through the primary winding, and that is the magnetizing current and the produced of magnetic flux, that would be in a same angle, right? Now as such there is no load and we consider this transformer as an ideal transformer, so primary winding behaves as an ideal inductor. So here the current is lagging by angle 90 with respect to applied voltage V1, right? So here IM current is lagging by angle 90 with respect to V1, so that will be shown here, right? Same way here, as such there is no flow of current I2, so induced EMF of E2, which is same as V2. So you can say this here, but the induced EMF in a primary winding, it is exactly in the opposite direction of applied voltage V1 as per the Faraday's law and Lenz's law. So you can see here the vector of E1, which is exactly in the opposite direction of V1, and in this direction you will also get the induced EMF across secondary winding same as V2, right? So this is what the phasor diagram of ideal transformer with no load condition. The same thing if we discuss about the with load condition, then you can see, so one of the current component you will get here, which is nothing but because of the small iron loss as well as a small copper loss, and that current component we define as IW is equal to I0 into cos 50. Current component we define here, that is my magnetizing current. That is nothing but a magnetizing current that will produce magnetic flux in the transformer, and that particular magnetizing current is defined as Im is equal to I0 sin phi 0. Now this is the same thing if I want to depict in form of the phasor diagram. You can check here, there is a magnetizing current in a same axis of the production of magnetic flux, right? So this is one of the current component, that is we define as Im is equal to Io sin phi 0. Same way here IW, that particular current we are getting because of the small losses in a ideal transformer when you connect the load. So the total current IO, so here the ideal transformer with load, the total current which is flowing in a primary winding we define as IO is nothing but the vector summation of IW and IM. So here you can see obviously the IO is nothing but the vector sum of IW and IM, that is defined as IO is equal to IW into IM. So that you can see from this vector diagram where we have taken two vectors Im and Iw. From this use the parallelogram method, and this diagonal shows the magnitude of Io. So this is what the phasor diagram of ideal transformer with load. Right now ideal transformer is never going to be a kind of practical transformer, because in your industrial application or residential application, whatever transformer you are using, all transformers are the practical transformer. So now let us discuss about the practical transformer to be more specific, where if we talk about the practical transformer without load, so there is no sense, because the practical transformer has to be with the load condition. So here in a practical transformer you are going to connect three types of load. One of the load we define as a resistive load, another load we define as a inductive load, and the third load we define as a capacitive load. So let us discuss about the practical transformer. So first we are going to consider about the working of practical transformer, right, in a load condition. So you can see in this particular figure where we have applied V1. Because of V1 there is a flow of current I1, and again there is a flow of current in a primary winding, so there is a production of magnetic flux. So if we consider a complete cycle, let's first discuss, once you apply a V1, then there is I1 flows in a primary winding, so the production of magnetic flux phi 0 is possible. Now so flux will induce EMF in a primary winding as E1. So magnetic flux is also linked with the secondary winding, as this particular EMF is called the mutually induced EMF in a secondary winding as E2, and as load is connected, so now I2 is flowing in this particular node. So if the I2 is flowing in this particular load, that means here the current direction of I2 is in an opposite direction. So since it is in an opposite direction, so that I2 current will also produce magnetic flux phi 2, which is in an opposite direction of magnetic flux phi 0. Right, now see here two magnetic fluxes phi 0 and phi 2 are in opposite direction. So here as a part of transformer designer, you have to compensate, or you have to remove the flux produced by current I2, which is phi 2, right? So to remove this phi 2, now we have to add the extra current in a primary winding I2 dash, and that I2 dash will again produce a flux phi 2 dash, which is exactly in a opposite direction of phi 2 and having the same value. So this phi 2 dash and phi 2 will be nullified throughout the this practical transformer operation. So here you can see as load is connected to I2, so flowing in opposite direction, so that opposite direction current will produce magnetic flux phi2, and this is in opposite direction of 50. So to compensate this reverse effect, to add a more current I2 dash to produce phi2 dash at the primary winding. So as it is resistive load, so E2 and I2, so if it is a resistive load and the induced EMF in a secondary winding and current flowing through this load, both are in the same direction, so both are in the same phase, right? If both are in the same phase, you can see here this line is for the flux line. So this is a phasor diagram where this is a V1, which is nothing but now this is a practical transformer. So here I0 is always lagging by angle 50 with respect to V1. Exactly in opposite direction you will get E1 as well as E2, and hence here you can see E2 and V2 both are parallel to each other. So vector is also represented as V2. Within same direction you will get the I2, right? So here E2 and I2 within a same angle you are getting, and with this respect, if I want to nullify the flux phi 2, because this is because of produced by current I2, I have to add the same value of current in a primary winding as we define as a I2 dash. So you can see this is a one of the vector having the length as the same length. I am going to apply I2 dash, which is in opposite direction, so that I consider as a I2 dash, right? Now at the input side, your I1 is nothing but the vector summation of IO, which is called a magnetizing current that will produce a magnetic flux phi 0, and I2 dash that will produce magnetic flux phi 2 dash that will nullify the effect of phi 2, and finally this is nothing but I1 vector summation of IU and I2 dash. So you can see from this phasor diagram using the parallelogram method by giving this two vector IU and I2 dash, and using this parallelogram method you will find the value of I1, right? So this is about the practical transformer with the resistive load. Now this same terminology, same operation if you apply, and if you are going to change the load, let us say you are going to change the load, and load it becomes now inductive. So here the practical transformer with inductive load, and now this load is nothing but giving with the RL load. So here I am going to connect resistance and inductor both. So in this condition now what should be the phasor diagram, right? So our operation would be the same, where you can see here in the phasor diagram. Now since the load is an inductive, so here I2 current which is lagging by angle phi 2 with respect to E2, right? So this is not the same case resistive load, because in resistive load E2 and I2 both are in a same direction, so both starts at the same angle. But here as such this is an inductive load, so I2 which is lagging by angle phi 2 with respect to E2, right? So to compensate this, I2 will produce a magnetic flux phi 2 which is in opposite direction of phi 0. To compensate this, phi 2 dash will be produced by adding extra current I2 dash at the primary winding, right? So this is what in opposite direction of I2 you can see the I2 dash, right? So this is what it is depicted like here. Draw V1, E1 and E2 as before. Now draw IO making an angle phi O with V1 and IO lagging by V1. So here IO is lagging by V1, as such the primary winding is a inductive winding which is a practical transformer. So you will get this, and after that draw I2 lagging behind E2 by phi 2, right? As such this is an inductive load. So now draw I2 dash exactly in a phase opposition with the I2. So we have drawn here I2 dash which is in opposite direction of I2, and from this now you will get total two current components I2 dash and IO, and by using the parallelogram method you can be able to find current I1 for this practical transformer in inductive load. So from this you can be able to draw the total primary current as the vector addition of I2 dash and IO, right? So this is a complete phasor diagram of practical transformer with inductive load. Now let us talk about the practical transformer with the capacitive load. So where again as such this is a capacitor, so its load is made up of resistance and capacitor, where here current is leading by angle phi 2, right? So you can see here I2 which is leading by angle phi 2 with respect to E2, right? So again the same terminology, to remove the effect of phi 2 we have to add extra current I2 dash so that the production of phi 2 dash is possible, right? So again in opposite direction you will find I2 dash. So this will be depicted here. As you can see here, draw the vector IO making an angle phi O with V1 as IO lagging by V1. As you know, this is a primary winding, so here IO is always lagging by V1 with the angle phi O, right? Then we have to draw I2 vector which is leading behind the E2 with respect to or by angle phi 2, right? And draw I2 dash in exactly in opposite direction within a with the same magnitude, and then you can be able to find now the total current which is flowing in a primary winding I1, because now you have a vector summation of I2 dash and IO. So here the total primary current is vector addition of I2 dash and IO, right? So if you recap the complete term in a practical transformer with load, so we have total three loads application is possible. One is the resistive load where E2 and I2 are on a are in same phase, right? Same way here in a inductive load E2 is lagging by angle phi 2 with respect to E2, and in a capacitive load you can see the I2 which is leading by angle phi 2 with respect to E2, where all this from this phasor diagram you can be able to calculate the current which is flowing in a primary winding, right? Thank you very much dear student. If you find any difficulty, please write in a comment box. Thank you very much.